nanohole through the chip and then force the DNA molecule strands to go through it by applying electric field, and you have a series of metal and insulators, it's like bands, that as this goes through, you make them stop, you interrogate, and then you make them stop and you interrogate. You basically get your C, A, G, T, and all that. So this could be a breakthrough, as you think it is, for very, very, very fast DNA profiling, the DNA identification, and leads to a lot of very interesting situations with genomics and so on, which at very, very low cost and very fast. So that was just the lower level as far as the devices. Now talking a little bit about the workload optimized systems and what's going to happen when we go from today, which you think about the petaflop regime computing, that's where the supercomputers are, to again the next phase, not next phase, for the next 1,000x again between 8 to 15 years of exascale, where it's a 1,000 petaflop computation. So what I'm showing here, again I apologize, you can't see almost anything here, so let me just describe it a little bit. So the top line is the high performance computing regime, or HPC, and those are actually IBM HPC machines. And very interestingly, what you can see is many of those attributes to parallelize and do application optimization that we started in the HPC world, we have taken it and put it into our commercial applications, Z and P, very specifically. And you can see, for example, if I pick the one Roadrunner, which was the first petaflop machine in the world in 2008, was the first incident that we actually created a hybrid structure where it uses cell processor as well as x86 Optron processors together to create that petaflop machine. But so more important, other than what was the original processor design, is the fact that we could do that, and by the workload optimizations that we did on the layers of the software, as I mentioned, you could actually create a very, very powerful machine at very, very low power dissipation. And we've taken those concepts of hybrid computing into our Z enterprise, where now you can do, of course, your OLTP type of data center applications, as well as additional appliance applications, for example, the data power that we do for XML processing, various ESP accelerated functions as well. So that's a very, very high value to take from that, and from those HPCs into our commercial applications. So basically what this chart is saying is this concept that I said, this is a top to bottom stack optimization. It is not a single technology optimization. You have to look at all of it at the same time and co-optimize the layers together. Now, what happens when you do that? So think about it on the left-hand side, which is today. Top is that another petaflop machine, which actually we've done more than one. I'm saying more than one system architecture, and combine that with those capabilities in the middle at the integration level, all the way from silicon to the software and application. You will get to a point that the whole petaflop, which was a 72, in that case, BlueGP rack, becomes 1/3 of a rack. So when you think about, let's say, a Watson type application, that today is like 10 racks of Power 7 using, I don't know, anywhere from 5 to 7 kilowatts, it'll become a box this big. I would say definitely in 15 years, probably sooner. So that, but to do that, you really gotta do all of those layers together. That's the thing I'm going to emphasize over and over again. Now let me get to the big data. So what's so intriguing about that? the fact that we are moving from big data today to a big fast data where not only you're increasing the volume by orders of magnitude, but you're also wanting to reduce the latency. So this is a plot I think is generally accepted. And so the origin of this is from Ericsson, Intel, Gartner, and other sources, which basically by 2020 we will get to 50 billion connected devices. And today we are about, let's say, 7, 8 billion. And very importantly, this includes machine to machine. So not all of this is generated by humans. A lot of it is unstructured data generated by devices, sensors, as well as GPSs and various other devices. So what does this do? The next two charts, I'm going to try to explain this.